All right, done. Not fun when you don't have a lab partner. Okay, you need to show up next time. Okay, and he's hit not enough hands to do all that stuff, but it was a pain. But we finally did get it. You can see the first, earlier I said the first data point was 0.90. It was not because it was tilted a little downhill. So once I put the, whoop, now we got a faster velocity out of it once we overcame having to go uphill. So the numbers are different. So here they are. Copy these down. Why don't you take a photo of it and send it to us? No. You know what? No. I'm not going to... What, you want me to do everything for you? Come on. Would you like some coffee? Maybe a donut. I have some pillows for your back. Is there anything else you need? Okay. So with babbling on, you can see those data points. Okay? 0.95, 0.91, 0.85, 0.79, 0.73, 0.66, 0.58, 0.49, and 0.37. And I did not do the 2 gram, just the dangly hooky thing, because it is too much slack and it rubs along and causes friction, so it would be a skewed point. Sometimes it works if I have a pulley with no friction. Oh, and that's one of the other things too. That pulley that we had, okay, here it is. That's the pulley I was using. I just took it off. And if I do this, it does some spinning there, but look what happens. There's friction there. So there is going to be some friction in this lab, even though we're eliminating it, a lot of it we are. The air track has hardly any friction, but there, maybe a little bit, but there's hardly anything. It's basically almost no friction. We can call it negligible. But this bad Larry here, the wire's got to go over that. And you can see it doesn't spin forever because there is friction there, and the wire in the mass has to overcome that friction to pull that cart. So what we're going to do, and you might say to yourself at this point, what's the point of this lab? I mean, what are we even doing? Okay, you can see from the handout that the purpose is to determine the mass of the air cart using F is equal to ma. Here's the thing. If F really is equal to ma, okay, Newton's pretty smart, but you know what? We have to verify and test. We have to verify. We have to do experiments. And science is repeatable. Just because somebody says something is true, okay, we have to back it up. Can other people do the experiment? Can other people use it to predict things? Can other people use that information to get the mass of something or whatever? So science is repeatable. So we are verifying this. We are verifying that Newton's second law is F is equal to ma. Okay, we have to be able to do that. So here's what we have. Okay, you have F is equal to ma. Okay, FOMA, Newton's second. We're using this, if it's true that F is equal to ma, then we can use it to get the mass of an object. As long as we know how much force we're applying to the object, and we can get an acceleration of the object, we can figure out how massive it is. We should be able to do that. So if we want to solve for m is equal to F over A. All right, okay, all right. So that's what we're going to do in this lab. We're going to use this second law to calculate the mass of the air cart. Now, you can see over here that I have the air cart mass already written down for you, 300 grams or 0.3 kilograms. Okay, those are standard masses for that air cart with those pieces on it and the 2 little silver masses that you might have saw, but I've noticed that were on there. So that is 300 grams. All right, so that's the true value. So what we're going to do is do an experimental value using our data that we gathered and compare it to the true value and see how much we are off. But I should never guarantee everything, but I will say virtually guarantee that when we get a mass calculation for how massive that cart is, it'll be bigger than 300 grams or bigger, larger, higher than 0.3 kilograms. You might say, well, why is that? Why is that? Some of that force pulling the air cart has to be used to overcome friction. So our data is going to make it look like the air cart's heavier than it really is because some of the force is being used to overcome the friction and not moving the mass of the air cart down the track. So it's going to virtually guarantee you'll get a number that's greater than 0.3 kilograms. Okay, typically I've done this enough times where a lot of times it'll end up between like 0.32 and 0.36 kilograms. I don't know where our data is. I honestly don't know. I haven't done anything with it. I just finished, put it up here. Okay, you're going to figure it out. Usually we get a mass that's heavier And maybe 0.31 to 0.36 kilograms is a typical range. Well, we'll see where we fall. And there's not a lot we can do about it in terms of experimental error. We do have some friction. We're assuming none. So, but based with some experimental error and some friction, all right, we will, if we know that we can predict that we should get a slightly heavier mass, then we can still verify that this bad Larry law is true, because with friction, then it still comes out pretty close. We'll get a percent error, and hopefully we'll get somewhere, under 20%. I don't know. We'll find out how much friction was in that pulley. I picked one. I had some pulleys that had a little less friction, but I picked one. I had one that actually had more. I said, no, I'm not going to do that. But I picked one that kind of had a little bit in the middle of the friction in order to try to get a number actually that is larger than 0.3. I wanted to get a number larger than that so we can make that point. Not everything in experimental science comes out to be perfect. Okay. All right, anyways, I've been bantering. I hope you've copied this all down. Now what you're going to do is you're going to take your data table, or your sheet. You're going to look from the data table here. We're going to look down here. There's a calculation table. You have to make a calculation table from the data. You're going to do these calculations, and you're going to put those results in this table. Those results in this table. All right, I will go through a couple of examples for you, so you can go ahead and you can do that. Now, okay, let's see. I'll get rid of this. I'm going to do a couple of examples for you, so I don't need all the data. I'm not going to do it. No, I'm not going to do it all for you. No, lab partner, you have to help me out. So your calculation table, okay, is going to look like this. Trial 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 trials, accelerations, and weights. Okay, well, let's see, what does that mean? Okay, so trial. So here's my calculation table. Trial 1, trial 2, trial 3. I'll do 3 for you. Actually, I'll 1, 2, 3. I'll go down to trial 9 on here. Now, I'm not going to do 9 trials. That would be all of them. I'm not going to do that. So I'm going to take this 3 out. So I'm going to do trial 1, trial 2, and trial 9. I'll do those 3. And so you do all the rest in between, lab partner. Come on, you got to help me out here. So trial number 1, 2, and 9, I will do the calculations for. Okay, take it through that. And we have to first, we are going to calculate the acceleration, and that's in meters per second squared. And we are going to calculate the force of weight, and that's going to be in newtons. All right, so let's go through this. Actually, I'll calculate the force of weight first. It's easier. And now there's a reason why I put it in the data table like this, because this is when we're going to graph this data. We're graphing this. This is x, y. And so I want this in the y position, so it's going to be on the y-axis. But I'll do the data here first. Okay, what do we do? Very simple. How do you get the weight of anything? Mass times gravity. Mass times gravity. Come on, you know that. Mass times gravity. So to get the weight, now that weight that I'm referring to is the weight that's causing the acceleration. We'll turn this, and it's the weight here that causes the cart to accelerate down the track. The reason the cart accelerates is because of this force of weight acting on those masses. Those masses are the force, when we multiply by 9.8, to make the cart accelerate, causing the acceleration. So we need to know those masses and how much they weigh, because we need the force. Remember, Newton's law is F force equals ma. So what weight were we using? All right, turn you back over this way a little bit. Okay, trial 1. We use the hanging mass of 0.02. So force of weight equals mg. So force of weight equals 0.02 times 9.8. You do the math on that, you'll get 0.196. 0.196. Okay, trial 2. For all 10 trials, lather, rinse, and repeat. Just like your shampoo directions. Do it over and over again. Keep going. Trial 2, 0.018. 0.018 times 9.8. 0.018 times 9.8. They actually did do that one out for you. 0.176. 0.176. Okay, I'm not going to do 3, 4, 5, 6, 7, 8. You do that. You fill in the data table. Trial 9. Okay, the last one, I already did that one out down here. I did it trial 9, trial 9, trial 9. 0.039. That would be 0.039. And just to verify, it'll be 8. Now remember, the mass used for trial 9 was 0.004. So that would be 0.004 grams, 4 grams, or 0.004 kilograms, times 9.8. So, there we go, 0.004 times 9.8, boom, 0.0392. But you're not going to be able to accurately graph that out there in the 10,000th place. So 0.039. So 0.039. So we have out to the 1,000th place. So fill these into the 1,000th place. We now have, once you've done the other ones, we have all 10 of the weights that we're going to need for our graph. Now, how do I calculate the acceleration of that air cart? Now, the air cart starts at 0. You know, I held it there. You saw that. Let it go. Okay, then it picked up speed. Let it go. Let it go. Some of you knew that was coming, didn't you? Mm-hmm. Yeah, you're starting to think like me. Kind of scary. Yeah. And so it went down the air track. That's the Grinch music when the Grinch goes down the hill heading into Whoville. Yes, it is. So we accelerated through the air track. We stopped it. So it accelerated. We need to know what that acceleration rate is. So that has to be calculated. Hence, in the calculations, you have to calculate that and put it in the calculation table. Okay, well, how are we going to calculate the acceleration of the air cart? All right, you're going to have to use one of the big 3. They don't go away. So, I mean, we'll refer back to them many times, several times in the semester. One of the big 3 is going to help us solve for acceleration. Now, all 3 of them can help us solve for acceleration. Acceleration is in all of them. However, we have to think of the information, the data. What data do we have? Okay, if we go back to here, we have the initial velocity, started at 0. We have the final velocities, and we have the distance it traveled. We didn't do anything with time. There was no time. So I need an equation with no time that'll solve for acceleration. The third one, the square root one, will do it. Yes, square root one. Can you see me over here? Come on, people. Come on, stay with me. Stay with me. Wake up. Wake up. All right. So I know that VF is equal to square root of VI squared plus 2AD. There it is. So let's plug in some information. Well, actually, let's solve it for A. Let's solve it for A. How would I find A? Okay, A, square both sides. So that would be VF squared equals VI. Now, VI, remember, was 0. VI was 0. It started from rest. That goes away. So VI is gone. 2AD. 2AD. We're solving for A. So VF squared divided by 2D equals my acceleration. That's how you are going to calculate the acceleration of the air cart. You have this information. The final velocity was given by the computer. The distance was 0.8 and for every trial, and then multiply it by 2, so 0.8 times 2 is 1.6. So for every trial, here's what you're going to do. I'm removing this now and just putting 2 times 0.8 or 1.6. There's your equation. You just have to do it 9 times. You have to do this 9 times for each one of the 9 trials. I'll do one with you here. Let's go ahead, lab partner, and show you. Okay, for trial 1, the acceleration is VF, which is 0.95. So 0.95, don't forget to square it, 0.95 squared. So 0.95 times 0.95, enter. Divide by 1.6, because that's the 2 times the 0.8. Divide by 1.6 equals 0.564. I'll go to the 1,000th place here, 0.564. So the acceleration, 0.564. Okay, we'll do number 2 together. Together, lab partner. Here we go. I'm going to take the velocity, 0.91. 0.91, and multiply it by itself, square it, divide it by 1.6. For every trial, divide by 1.6. 0.518. 0.518. Okay, you do 3, 4, 5, 6, 7, 8. I'll do 9 down here. Okay, I need the velocity for 9. Now I erased it, but of course, I did write it down, of course. Earlier we had it 0.37. So 0.37 is the final velocity for trial 9, times 0.37, enter, divided by 1.6, 0.086. 0.086. Okay, lab partner, you make sure that you get all the other trials done in here on your data table. You go ahead and you do that, and once you've got that done, we'll reconvene and we'll go to the next step. All right, I'm waiting for you. Hurry up.